Welcome back to The Explainer. Today, we're skipping the traditional agenda because honestly, I just want to throw you right into the middle of a classic coding nightmare. Just imagine you're in the hot seat of a high-stakes technical interview. The clock is ticking down, your interviewer is staring right at you, and you are faced with a seemingly simple data problem that's actually, well, it's a trap just waiting to spring. Section 1. The Brute Force Trap. Let's set the stage. Imagine you're handed this massive array of numbers, and you're going to be hit with multiple queries. Each query asks a really simple question. How many times does this specific number appear in the array? Sounds pretty easy, right? Okay, let's dive into this. If the query asks, hey, how many times does the number 1 appear here? What's the very first, most naive approach that pops into your head? Well, if you're like most programmers, you're immediately thinking about looping. That naive brute force method looks exactly like this. You take the target number, you loop through the entire array, and every single time you see a match, you increment a counter. Then you just restart that whole process from scratch for the next query. Simple enough. But what if the array has 100,000 numbers? And what if the interviewer throws 100,000 different queries at you? That's 100,000 multiplied by 100,000. Suddenly, you're looking at 10 billion operations. 10 billion. Let's break down the shocking math on that. In standard competitive programming environments, a machine processes roughly 100 million operations. That's 10 to the power of 8 in about 1 second. So if your brute force nested loop requires 10 billion operations, your code is going to take a whopping 100 seconds to execute. And man, if you've ever coded competitively, you know the absolute stomach-dropping dread of seeing these 3 words. Waiting. Over 1.5 minutes for your program to run basically guarantees a time limit exceeded error. It is an instant failure. So we clearly need a completely different paradigm to solve this. Section 2, hashing, pre-store and fetch. To stop reacting to every single query with a painfully slow loop, we've got to be proactive. We need a massive shift in how we handle our data. So the crucial point is, hashing is simply pre-storing and fetching. That's it. Instead of counting numbers right when we're asked, we do all the heavy lifting beforehand. We create what's called a frequency array, where the index of the array represents the number itself, and the value at that index stores how many times we've actually seen it. So when a query asks, how many times does 3 appear, we literally just look at index 3 and instantly fetch the answer. No loops required whatsoever. But hold on, here's the catch. We have hard, physical memory limits to deal with. If you declare an integer array inside your main function, you can only make it up to about 10 to the power of 6 in size. Now, if you declare it globally outside of main, you can push it to 10 to the power of 7. But think about what happens if your interview problem pushes numbers all the way up to 10 to the power of 9. Attempting to declare an array that unbelievably huge, it means an instant crash with a segmentation fault. Section 3, hashing characters with ASCII. Real quick, before we solve that massive number problem, how do we handle strings? Our frequency array relies on indices, right? And those are purely numeric, 0, 1, 2, 3. So how in the world do we map a character, like the lowercase letter f, to an integer array index? Like, how do we turn the alphabet into pure math?
And this brilliantly illustrates the solution. You see, every character in coding has a numerical ASCII value. For example, a lowercase a is exactly 97. So if we take any lowercase character and mathematically subtract a from it, the compiler automatically casts them to integers for us. So a minus a is essentially 97 minus 97, which perfectly gives us index 0. Subtract a from f, which is 102 minus 97, and boom, we get index 5. It's almost like a magic trick.
And what's absolutely amazing about character hashing is that it is completely safe from those memory limit crashes we were just talking about. If a problem only uses lowercase English letters, your hash array only needs to be a tiny 26 spaces long. Even if it uses literally every weird character on your entire keyboard, the maximum possible size is just 256. So array hashing is for sure always perfect for characters. Section 4, breaking limits with maps. Okay, so what do we do when our numerical data explodes past that 10 to the power of 7 limit? How do we hash a number like 1 billion without our computer just bursting into flames? Well, enter maps. In C++, these are part of the standard template library, or the STL. Maps completely solve our memory limit problem because, unlike arrays which stupidly create empty spaces for every single number from 0 to 1 billion, a map only stores the elements that actually exist in your array. It links a specific key, which is the number you're looking for, directly to a value, which is its frequency. But You do have a choice to make here, and it is a critical one. On the one hand, we have the standard map. It stores keys in a perfectly sorted order, and it takes ov login time to fetch your data. Pretty good. But on the other hand, we have unordered underscore map. It stores keys totally randomly, but its average fetch time is O of 1, like literally instantaneous. As a general rule of thumb, you should always prefer unordered underscore map first, simply because of that blazing fast O of 1 speed. But did you happen to notice that little asterisk next to it? Yeah, the dreaded O of n worst case. Let's talk about that.
Section 5, Under the Hood, Collisions.
To really understand that worst-case scenario, we need to look under the hood at how unordered maps use what's called the division method. How exactly is it mathematically compressing giant numbers into tiny memory spaces? Well, let's say your computer's memory restricts us to just 10 storage slots. If I give you the number 28, the map takes 28, modulo divides it by 10, and just looks at the remainder. The remainder is 8. So it securely stores the key 28 right there at index 8. It's honestly a genius way to squeeze big numbers into super small limits. But watch how this builds when things go wrong. What if you try to store 18, 28, and 38? Well, all three of those numbers, when modulo divided by 10, leave a remainder of 8. They all want to live at index 8. This right here is called a collision. Under the hood, the map has to handle this by building a linked list. It attaches 28 to 18 and then 38 to 28, forming this linear chain branching right off that single index. And that brings us to the absolute nightmare that is the O of n worst case. Imagine your interviewer gives you a brilliantly malicious test case where absolutely every single number they give you collides at the exact same index. Instead of an instant O of 1 fetch, your poor program has to slowly crawl through a massive linear chain of elements just to find your answer. So suddenly, your ultra-fast unordered map becomes just as slow as the naive brute force loop we started this whole explanation with.
So I'm going to leave you with this final test of your new knowledge. You're on the clock. You have exactly 10 seconds to fetch 1 billion unique strings. Do you gamble on the blistering average speed of unordered underscore map, knowing full well a malicious test case might cause massive collisions and completely ruin your runtime? Or do you play it entirely safe with the slightly slower but incredibly consistent logarithmic time of the standard map? Understanding that specific trade-off, that is exactly what separates a good coder from a truly great one. Thanks for tuning into The Explainer, and I'll catch you next time.